All right, so first of all, as an overview to your Ambridge, nicknamed Ambridge, the idea is that we want to make it easy to link uncertainty quantification tools and numerical models, could be simulation softwares. Um, this starts at simple prototyping and goes all the way to high performance computing and UQ benchmarking and a bunch of related topics that this plays into. So first of all, for those who are new to uncertainty quantification, we are mostly focusing on uncertainty quantification of numerical models, and that typically means something like a parametric uncertainty. So we can refer to the US National Hurricane Center for an explanation. They tell people not to focus on the skinny black line that you have in the center of this hurricane forecast, but they tell people to look at this entire wide cone of possible paths that this hurricane might take given current best knowledge. And that's really the point. Even if we have a perfectly accurate numerical simulation model for a hurricane, we are still not going to know exactly where it's going to go if our initial data is incomplete or affected by measurement errors. And when you think about it, pretty much all data that we have is affected by errors of some degree. So in the end, what we are looking for is not just a single prediction, but in fact, an entire range of possible predictions that seem likely given the current best information. And that's a bit hand waving and intended to give you the general idea. But this can also be done, or the idea of uncertainty quantification is to do this in a sort of statistically accurate way. And most importantly, what separates it from just plain statistics is that uncertainty quantification methods specifically aim to um, essentially incorporate knowledge about the fact that they are using some numerical model in order to accelerate. After all, many statistical methods, like Monte Carlo, for example, might assume that you might be able to do millions of evaluations. But as we've already seen in the talks before, for example, in Delphine's talk, the simulation models that she's been talking about, that's absolutely not possible to do that. And one workaround could be building these surrogate models or emulators that she briefly described, or just generally any method that somehow tries to incorporate some knowledge about the fact that we have simulation models. All right, so that's a very broad overview. This example is specifically uncertainty propagation. So we start from an uncertain parameter and we propagate that through the model, getting a bunch of, or an entire range of predictions, an entire distribution of model outcomes. There's also the opposite direction, if you will, also known as inverse uncertainty quantification. Specifically, it's often Bayesian inverse problems. In that setting, the idea is that we have some real-world observations. In this example, we have some buoys basically floating in the water off the coast of Japan. Those record water heights, and from those observations, we would like to infer an underlying parameter. For example, the source of a tsunami, which could be anywhere in the water here. And we would like to use our simulation model as a way to essentially track back from these observations that we have all the way to where the tsunami originally came from. In this particular example, you see that there's specific simulation software involved, which in itself is pretty intricate. And already here we see an example of what the distribution of possible tsunami origins might imply as for possible results that we see in the end. And you see that essentially the UQ method here tries to replicate the observation that we have using that simulation model. So that's roughly how inverse UQ is performed. You start from an observation, we try to find the underlying distribution of plausible parameters. All right, so that's broadly the categorization of things that you would find in uncertainty quantification for numerical models. There's, of course, also uncertainty in does your model actually match proper physics, or some very other settings where, for example, in machine learning, you might want to understand uncertainty, but those are separate topics closely related, but not our main focus for at least this introduction here. So that's UQ problems. How do we solve them? And solving UQ problems means we try to find these distributions that are implied by uncertain data. So it could be the distribution of hurricane paths. It could be a distribution of origins of a tsunami. How do we find them? There's a huge lot of algorithms, and we've already seen a couple of those in Sergey's and Delphine's talks. The reason that there's an entire zoo of methods is that these methods fundamentally differ in how model agnostic they are. So some of them actually require you to change the model formulation itself or the problem formulation itself and really dig deep into your simulation software. They differ in what they tell you about the problem. Some might just give you some highest probability, others give you maybe an expected value, others might give you samples of the entire distribution. And of course, they differ in how efficient they are. The problem is that we really can't have all three at the same time. So a method that knows nothing about your model, that tells you everything about the solution, and that is very fast to compute is obviously something we can't have. So you have to somehow pick between these goalposts basically and find your own balance. Each of these is going to lead to a certain method here. I'm going to give you a quick idea of a specific uncertainty quantification method. So that's Markov chain Monte Carlo. It's a very basic method for Bayesian inference or for inverse uncertainty quantification. So essentially we are in that setting of the tsunami, right? We have some real world observation. We want to know some underlying parameter. The idea about the Bayesian inverse problem is to say a parameter is likely, indicated by blue here, if the corresponding model prediction comes close to the data that we've observed. So in the tsunami setting, that would mean if we let our tsunami start somewhere in this region, the outcome that our simulation produces is very close to the observed buoy data. Somewhere out here, for example, the tsunami would lead to a very different prediction, and we therefore say this is most likely not the true parameter or most likely not the origin of the tsunami. Formulating it like that, we can really just do sort of pointwise evaluations of this underlying distribution, right? I mean, for a specific point, we can do the tsunami simulation, we can compare to data, and we can say this is likely or this is not likely. However, this sort of pointwise approach doesn't really give us the entire distribution. Getting the entire distribution is therefore the task of some kind of an algorithm. Markov chain Monte Carlo is a possible approach. So how does this work? Markov chain Monte Carlo starts with an arbitrary parameter, and it's going to evaluate the density at this point, which means we run the simulation, we compare to data in the Bayesian framework. As a next step, it's going to produce a random point in its vicinity, and it's either going to jump to the next point if it has a reasonably high likelihood, or it is going to reject the next step if it has a considerably lower probability. If we let this play out automatically, you see that over time, this is going to produce a sort of random walk across the entire parameter space that is slowly but surely going to approximate the underlying probability distribution that we are looking for. So the samples are going to converge towards that distribution. And that's great because, again, for point-wise evaluations, it allows us to retrieve the likely parameters. The catch is for each and every point that this algorithm looks at, we need to run the simulation and we need to compare to data. And running the simulation, again, can be very costly in some real applications. So this very basic Markov chain Monte Carlo is, well, provably converging to the solution, but the cost is often just prohibitive for any practical application when you're talking about costly models. So we need to come up with something more clever. This is just to sort of give you an idea of what this could look like in its most basic form. There's a number of ways how you can build on top of Markov chain Monte Carlo, and there are a number of other methods that you could look into as alternatives. However, and that's something we're going to have a look at, they have a few things in common and we can exploit that. All right, but for now, how would this Markov chain Monte Carlo play out for the tsunami problem? What we'll essentially get is a distribution of possible origins where that tsunami came from. Just to quickly mention, because that's something that I've personally been working on and that we'll use as an example later on. One way how you can accelerate Markov chain Monte Carlo is by introducing a hierarchy of approximate models that give you a hierarchy of approximate solutions, of approximate distributions that come out of these. And for example, multi-level Markov chain Monte Carlo or multi-level delayed acceptance would then exploit that fact or this hierarchy of models so that they only have to do very few steps on the fully resolved costly model while doing thousands or millions of samples on very fast, very approximate models. All right, so this is just to give you an idea of how you could approach uncertainty quantification problems, possibly with a more efficient algorithm by going through a level hierarchy or possibly going through some other routes. So now that we have successfully solved the UQ problem for a rather costly simulation code, and this still took us a couple of thousand processor cores, you might of course ask the question, can we immediately apply this to some other problems? And first of all, there's some good news. So when you think about this Markov chain Monte Carlo approach, we are really just evaluating the Bayesian posterior pointwise. In other words, for every point we run the simulation code, that's something we can do. We get an output, we compare to data, and that's it. So strictly, this algorithm only requires us to do simple model evaluations, where we just say model is a mathematical function, taking some input parameter to some outcome. In this case, taking the source of a tsunami, just two numbers, 2D vector, onto some predictions about what these buoys would observe. So this is a very basic interface, and that should apply to a lot of different models. Pretty much anything you can plug into this. Other UQ methods that try to be a bit more efficient by exploiting gradients might, in addition, need, of course, gradients, might need Jacobian actions, Hessian actions, but a lot of UQ algorithms really just need this kind of common mathematical interface. There definitely are exceptions, but for a lot of UQ algorithms, that already works. So you might say there's this sort of simple model agnostic interface. Let's just apply it to a lot of different models and solve interesting problems. Reality begs to differ, unfortunately. In practice, when we are working with complex simulation codes, it becomes tricky to hook those together with uncertainty quantification codes or pretty much any sort of higher level workflows, because quite often these codes are not actually built to be used in such a way. They often use very different tools than people in uncertainty quantification or optimization might use, simply because simulation codes need very fine level of control, whereas UQ tends to be not that compute intensive, and you might want to go with something like MATLAB or R or some sort of higher level language. There could be conflicts in how these codes approach parallelization, which can be quite a substantial problem. And quite importantly, you need to bring together experts from the UQ side and the model side in order to make that work. So long story short, quite often it happens that even though conceptually it's easy to apply some UQ methods to interesting models, we need to spend a lot of engineering effort and development time on actually building these applications in software and especially building the link between the two worlds. And this is time that we'd rather spend on solving more interesting problems, on improving the math, and so on. So we've got this discrepancy between how easy it should be to link the two sides through math and how easy it turns out to be in actual practical implementations. So I thought there has to be a better approach. In fact, this just came out of necessity in this Tsunami project. And we've since been following a very different route with UMBridge. The idea is that UMBridge implements this abstract mathematical interface in software. And in contrast to a lot of established UQ and optimization codes, we do not do so through a direct coupling in software or through writing files and launching codes, but instead we do so by essentially combining two entirely independent pieces of software through network communication. This is, I think, fairly unusual in scientific applications, However, in the software industry, there's essentially an entire boom of microservices that already happened some years ago, where this concept was really sort of established quite widely. We do get quite a few benefits from this. For example, programming languages don't actually matter anymore in the sense that both sides only need to speak that common network protocol and they can work with each other. What we get from that as a result is that on one hand, we can really just hook together arbitrary codes on either side. But on the other hand, because we settle on the specific mathematical interface that we have between UQ and simulation, it also means that it acts as sort of a single entry point, because it is enough to hook up a single UQ code to that Umbrage interface, and it immediately gets access to pretty much any model that you can throw at it. While on the other hand, if you have an interesting model at your hands, it's enough to implement the sort of model side interface of Umbrage, and you get an entire range of UQ codes to choose from and to apply. In addition, we also get separation of concerns because now each expert can focus on their respective field of expertise. And something that is relevant for at least a number of projects is that it is much easier to now scale up to cloud and HPC environments because we provide essentially general purpose platforms that allow you to easily take one of these setups here and scale it up by launching a huge number of model instances on a cluster, and Umbrage takes care of load balancing and essentially managing these instances, passing evaluation requests between both sides and so on. So this is really bird's eye view of Umbrage. We're going to go into more details later on. But first of all, let me give you a bit of an idea of what this might look like in practice employing Umbrage in an uncertainty quantification project. This is actually what we did for the tsunami application. Initially, we had been doing this through a classic high-performance computing cluster and making use of MPI and so on. But we've actually, oops, I think I've just lost connection. Okay, so I think I just briefly lost connection. I hope we're back now. I hope we didn't lose too much. So this is right. So this part is going to give you an overview of how Umbrage plays out in practice if you apply it in a real-world project. This is specifically what we did in this tsunami application. Again, in our first setup, we used essentially MPI and a classic bare metal installation on a high-performance computing cluster, which took us weeks and months to really just make it all work together. We set out to try this again with Umbrage, and in fact, it turned out we could do the entire tsunami application in something like, I think in total 3 days or so, because now we had this separation of concerns. So how did that play out in practice? First of all, Anna set up the simulation code on her system, testing just with some test scripts sending in parameters to that model and making sure that it produced the expected output. Because the test script could be any language, it could be Python, it could be Julia, whatever you like. And the model server itself, in our case, that's a code generation C++ simulation code, which is a bit tricky to handle. But again, by going through that Umbrage interface, it's quite easy to hook this up to some arbitrary test script and just see whether it does what it's supposed to do through that interface. So once Anna was quite confident that this model was actually doing what it was supposed to do, she could wrap this up in a container. So for those of you who are not familiar with containers, containers essentially allow you to wrap up your software and all of its dependencies and install it in something like a lightweight virtual machine, which you can then take as a black box and pass to other people. What's really advantageous for us here is that for Anna, it's really easy to set up this container because she knows the simulation code very well. She could then take this container and send it to Mikkel Lykkegaard, who will give a talk tomorrow. He is a UQ expert who is not familiar with that specific simulation model. However, because Anna wrapped it up in a container, That simply meant that he did not need to understand the inner workings of that simulation code and could still interact with it. So let's say he hooks this up to some simple Markov chain Monte Carlo method just for testing. Of course, solving a UQ problem on a tsunami plain Markov chain Monte Carlo is probably not enough. So let's do something more interesting and go multi-level. In order to make that work, you can, for example, spawn multiple container instances or configure the Umbridge model through some config variables. And again, just hook this up to a very different UQ software. In this case, we use TinyDA that Mikkel is developing, and he'll mention that in his talk. Now we've actually hooked this simulation code up already to 3 different codes, but there's absolutely no change necessary to the model side because it's all going through that unified interface. Likewise, we can jump between UQ codes here and swap them out as we play around with the model and get a feeling for it. Because again, the UQ codes just speak Umbridge to some model and don't care about any technical implementation details of the model itself. Now, since running this on a single machine is still not enough, I then took Linus container and spun it up on a cloud cluster on Google Kubernetes Engine, which allows us to run hundreds or thousands of model instances on large online clusters. Our setup that we provide, that we'll also look at tomorrow in more detail, then takes care of balancing incoming evaluation requests between a large number of model instances that we have running, which allows us to parallelize. So now the UQ code can actually send parallel evaluation requests, while the load balancer that we provide takes care of handling the distribution of these tasks to a number of independent model instances. What's really nice about that is, well, I'm familiar with Google Kubernetes Engine, so I could easily take Linus container and just tell our Umbridge setup to spin up these instances, while Mikkel is really not that familiar with it. However, I could just give Mikkel the address of our cloud cluster, and he could point his multi-level delayed acceptance code to that address instead of a model running on his own system. So to him, again, nothing changed except that model evaluations can now run in parallel and overall quite a bit faster than on a single system. Finally, if you want to get fancy, we added an additional accelerator in between. We've now developed a Gaussian process emulator as sort of a proof of concept that acts even as sort of a microservice. So it itself really just speaks the Umbridge interface to UQ codes, while also making use of Umbridge to request model evaluations if it needs to retrain and learn about a new parameter or a new area of the parameter space that it's not familiar with yet. And again, the UQ code doesn't even see a difference, except that sometimes the model evaluations come back much, much faster than they would from a simulation model. All right, so you can see that this is a fairly complex setup, but in contrast to the weeks and months of making something even somewhat simpler run, we could get this all done within 3 days because, well, each of the experts could really just focus on the main part that they are best at. We had a clean interface in between, so could easily swap out components. And through containerization, really only the person who is familiar with the model itself had to understand how to set up this complex piece of software. Everyone else can then fully focus on the more sort of data sciencey aspects of this. All right, so that's for the benefits that you can expect in some larger complex problems. Let's see how that works in practice. And I'm now going to give you just a very basic demonstration of how that tends to play out. And as part of the practical exercises that we'll have soon after, you can play through this yourself, and we have a tutorial that guides you through it. So this is really just a very quick demonstration to give you a rough idea. So let's first of all get started by running a model. So the model is actually technically a server. In other words, it's now just running on my laptop, idling, waiting in a loop until new evaluation requests come in. Mathematically, this provides the map from input parameter to output parameters that I mentioned before. A basic Umbrage client might look something like this. Ignore the first couple of lines. That's basically some Python boilerplate to accept an input from command line. The key part is that we, just similar to what Sergey already briefly showed for MATLAB, is that we get ourselves an instance of an Umbrage HTTP model, which is sort of the client UQ side of that link. We tell it a URL or an address where that model is running, and we give it the name of the model. In this case, the model happens to be named forward. We can then define a parameter that we might want to pass into that model. So that's just a vector. And we can then plug that vector into the model and print the output. Really, this is all. So in Python and pretty much all the languages that we support, evaluating a model is really just a function call and all the network stuff, passing that to the running model and getting back results. This is handled fully by Umbrage. So let's see how that works out. Let me make this a little bit bigger. All right, so I'm now taking this client that we wrote, or that we looked at, and I'm pointing it to localhost, my own system, because that's where the model is currently running. Let's give that a try. So this time we get the output for the input dimension of the model. That's one. We get an output for the output dimension of the model, and then we get an error. Because, and it complains to me, I have passed in a two-dimensional vector, but the model actually expected a one-dimensional vector. So let's quickly change that. So here's the input vector that I defined. Let's just change the input vector to something like 100. I'm now going to run the same thing again. And now this time it prints the output from the model. Now that's not particularly impressive, considering that I just called something in Python from Python. But let's try something different. For example, we can, oops, don't have a C++ compiler on my system now. Okay, sorry about that. So you just have to believe me. Basically, you can take any client in another language. For example, Sergey showed you before that you can use a MATLAB client, connect to it just like that. Again, because this is going through network, languages or specific frameworks on either side don't really matter. So alternatively, we can, for example, apply a UQ package to it. This is a code making use of quasi-Monte Carlo through the QMCPy package. QMCPy has a pretty nice interface. Most of the code that you're seeing here is setting up this quasi-Monte Carlo setting. The only thing that's slightly different is that, again, we are defining an Umbrage model that we want to connect to. And as an integrant for our quasi-Monte Carlo method, we are using an Umbrage wrapper, which is provided as part of the QMCPy package. As you can see, into this package, into this wrapper, we can pass in our model instance, so it's going to operate on that. All right, so that's how we connect to the model and how we make QMCPy aware of the model. As you can see, this is really nicely integrated with how QMCPy works. So let's do something with QMCPy. QMCPy allows us to define a distribution to sample from. It is going to generate samples from that distribution. It's going to apply the model to each of these samples, and it's going to collect the output that we get from that. In other words, it's pretty much like a Monte Carlo method for uncertainty propagation, except that it is a little bit more clever about how it performs sampling from that distribution. So let's say we want to sample from a uniform distribution on a range between 0 and 1. Now I'm going to run the QMCPy client and again point it to that model running here. This is now taking a little bit longer because it's doing quite a lot of evaluations of the model. And what do we get? We get a solution of 1. Does that make sense? Well, at this point, I'm going to reveal to you that this model that I'm currently running is a very basic thing that is really just multiplying a number by 2. We started from a uniform distribution between 0 and 1. So that uniform distribution itself has a mean of 0.5. The model multiplies by 2, so we get out a mean value of 1. So that is as expected. We can now start and play around with very different distributions in QMCPy, but that's something that we're not going to do here. You can try this out in the practical part afterwards. All right, so this has been just a very basic model that we've looked at so far. We can, of course, do more interesting things, and after all, that's what Umbridge is all about, enabling us to connect to more interesting models. So as part of Umbridge, we are developing a library of models and benchmark problems. You find them on the Umbridge documentation page. We can, for example, have a look at a tsunami model. This might look familiar from my talk. This is exactly the tsunami model that I mentioned before, so you can now also grab this model and operate on it. Since we provide this as a container, it is enough to essentially execute this command that we have here. And Docker is going to download and run this image on your system, and you'll have this tsunami simulation code running happily inside its container without needing to install it. So I'm now going to copy over the command. The only thing that's slightly different on my system is that I'm using Podman instead of Docker, but that's equivalent apart from that. All right, there's no download process because I already ran this on my system. On yours, it might take a while till it downloads the 2 GB or something that this model consists of. But most importantly, there's really no installation effort going on because we are going through containers. All right, now I promised you before that languages don't really matter once you go through Umbridge, since we are making use of network communication. This simulation code is in essence written in C++, or technically it's even some code generation system that spits out C++ in the end. So some fairly complex beast that would be very complicated to interact with from Python. But again, since we are going through Umbridge, I can really just use my previous Umbridge client and connect to it. This is the unmodified client that I just used for the simple multiplication by 2. Now it's giving me different output. It tells me that the input dimension is now 2 and the output is going to be 4. When we look at the documentation of that model, it tells us that the input are going to be the x and y coordinates of the tsunami origin, and the 4 outputs are going to give me arrival time and maximum water height for 2 buoy points. So that's all the information that we need in order to perform inverse uncertainty quantification with some MCMC related algorithms. Again, I'm getting an error because I passed in an input of wrong dimension. So let's go back to actually passing in a 2-dimensional input, which is now going to specify the origin of the tsunami. Let's run the client. And this time you see that I'm not getting back an error, but instead the client is stuck for a while. And in the meantime, the simulation code starts printing out a lot of log messages while it's actually propagating the tsunami and doing some heavy computation. You may have noticed, by the way, that the second computation took a bit longer, and it actually produces a slightly different output. Going back to the client, you see that in the second call, I'm actually passing in additional config options to the model. And importantly, I'm telling this model that it's supposed to be running at level 1 now. Again, referring to the documentation, we see that this model offers a config option named level, which essentially tells us, and this is going to be detailed below a bit more, which essentially gives us different discretization levels of the tsunami, which is also shown in the sketch here, right? Level 0 is going to give us a very rough approximation. Level 1 is going to be a bit more costly. And then level 2 might be something that you probably shouldn't be running on your laptop because it's a bit, it's a bit expensive for that. Anyway, so this shows you how you can also control some details of the model setup through Umbridge from whatever client you happen to be working with. We could now again apply QMCPy to perform uncertainty propagation on this tsunami, but at least within this talk, this is not going to be this is not going to finish. So we leave it at that, and you can jump in and try things out for yourself in the tutorial. All right, so this is right on time. So thanks a lot for listening. I'll now be happy to take any questions, and afterwards we'll continue with the practical session.